So hi everyone, we will try to start fast, try to do briefly. So welcome again to another seminar here in the Colloquium. Today I'm very proud to introduce my colleague, and it's an honor, Gloria Faraone, who is assistant professor here in the Department of Civil Construction and Environmental Engineering here at San Diego State. Gloria received her Master of Science in Structural Engineering at the University of Bologna in Italy. And then a couple of months ago, in June of this year, she also received her degree in her PhD in Structural Engineering here at the University of California, San Diego. Gloria's research experience includes full-scale structural testing and numerical modeling of the structural elements. Her research interests focus on the seismic behavior of concrete structure, as well as non-structural component and system. Today, she will talk about the seismic performance of a structural element. In specific, she will show us some models about shear walls and LiDAR technologies as damage sensing technologies. So, Gloria, thank you.
Thank you so much. Can you hear me? Oh, is it too loud? Okay. Thank you so much for the introduction, Ignacio. Thank you so much for inviting me here today. It's an honor and a pleasure to show you a little bit of my research, and with specific focus on what you can probably do, so how we can collaborate. I know it may sound boring to you, seismic assessment may sound a little bit boring, but there's a lot that you can do, and probably you're going to find it also fun, hopefully. So I'm going to show you, first of all, I'm going to introduce you to earthquake engineering. And then I'm going to show you in the specific the computational applications to earthquake engineering. So what can you do with your computational expertise? What can you do to help us as structural engineers to advance the seismic resistance of structures, reduce damage, and improve our infrastructures? In the specific, I will go through two main applications. One is the numerical modeling tools, and the other one is the laser scanning techniques. So let's look at this. First of all, why earthquake engineering? So I think the pictures can speak for themselves. However, earthquakes have a vast socioeconomic impact to a community due to the associated fatalities, monetary and downtime losses. A couple of weeks ago, Dr. Sepulveda showed us that tsunamis are really impactful for our coastlines, but the earthquakes can also cause fires. Like in 1906 in San Francisco, there was an after earthquake fire that was probably more devastating than the earthquake per se. And then they can also, of course, damage man-made structures like infrastructures, pipelines, buildings, and so on. And last but not less important, they kill people. Many fatalities occur. Here we see pictures of 3 key events that occurred in the late 80s, early 90s. The first one in Mexico City, 1985. Here in the middle, Northridge, 1994, Southern California. Probably you may know this. It was quite devastating. And this is Kobe in Japan, 1995. Just to give you an idea of, since we are engineers, we like numbers, 10,000 casualties in Mexico City. It was estimated around $90 billion, corresponding to the value of dollars in 2021. So the current value of money, $90 billion in damage during the Northridge earthquake. And about 6,000 fatalities during the Kobe earthquake in Japan. So broad impact of earthquakes. We need to do something. We as structural engineers, as earthquake engineers, we need to design better and safer structures, right? So what can we do? Everything starts by observing and documenting damage during and after an earthquake event. We can learn a lot from past earthquakes. We can look at buildings that withstand the earthquake, buildings that fail, and we can understand why one performed better than the other. So we can identify what what key elements we needed to design and build for safer structures. But you may understand this is limited because we always need an earthquake event to perform these observations, right? So it's kind of limited. We cannot, in some sense, we cannot wait for the next earthquake to come to understand better. So the other thing that we may do as engineers is full-scale testing. So we have a structural lab also here in San Diego State University. We have a small structural lab with a shaking table, really cool. And we can perform testing. We can design our own structures, test them in the lab, and see how well they perform. And you may wonder what a full-scale testing looks like. I'm going to show you just in a moment. So these are the walls that I tested, full-scale walls. So 16 feet high by 8 feet in length. This was the biggest wall that I tested. And these tests were performed at UCSD in collaboration with UT during my doctoral studies. And so I designed 3 full scales, two walls like this one and one like this one. You see they have a different geometry. One here is called the slender wall because if you take the ratio between the height over the length, you get a value of 2. And walls like these are called the slender walls. And they usually respond during earthquakes with a specific type of damage. So with we call it in a flexural way. So if you imagine this wall during an earthquake, you will get a majority of damage like this. So cracks that are almost horizontal. The second type of wall, so the second geometry is the squat wall here, this wall here. This is a squatter. It's a low aspect ratio wall. If you take the ratio between the height and the length, you get 1. And these types of walls usually behave more in a shear dominated way. So they develop this diagonal crack that can go from corner to corner, and they progress as the earthquake demand increases. So what did we do? So we had these 3 full-scale specimens. We applied a vertical load on top to simulate the effect of what you have above a wall. We have other structures, we have people, we have furniture. So these create a vertical load on the wall. So we applied this load here at the top. And we applied a cyclic displacement. So you see in this picture, there is a big arm. This is an actuator. It's a big arm that literally moves at the top of the wall to simulate earthquake loading. So we applied this cyclic reverse history displacement at the top to simulate the earthquake loading on the wall. And this is what it looks like. So I prepared this video. It's like a couple of minutes video, which summarizes all the full day testing. So these full-scale tests are usually very long. This test took us 12 hours, more or less. So we started at 5 a.m. in the morning. We went on till 10 p.m. in the evening because we load it and then we stop everything. We take a look at all the cracks, all the sensors, all the damage, and then we load it again and then we stop. So it was quite long, but it was really fun. And here we see everything in a couple of minutes. So let me explain. Here on top, we see one face of the wall with some connectors attached. So we wanted to simulate the effect of non-structural components attached to the wall during an earthquake. Like imagine panels or pipes. What happens to pipes attached to a wall during an earthquake? So we attached this element here on one side. On the other side, we had panels, instrumental panels. These are displacement sensors, which are basically screens that measure the relative displacement between points into the wall. And this is how we record our data. So this is how we collect data. Here at the bottom, we see the load versus displacement curve of the wall. And this is the applied displacement at the top of the wall. So the drift that moves the way, that moves the wall here at the top. And we see, as we saw before, this is the squat wall. So this is more shear dominated, and we can see indeed a lot of diagonal cracks that span from corner to corner. And this shows us that the wall behaved in a shear dominated way. And you can start seeing a lot of concrete crushing localized here at the bottom of the wall. Here we are now at about 2 inches displacement at top. And the wall is still holding the load. See, it's still quite at capacity. So it was a very strong wall. Now we can start seeing some more damage. What happens during this reverse loading? Basically what happens is that the reinforcing bars that are embedded in the concrete deform. So they get in tension and compression, so they deform this way. And after a while, they deform out of plane. They cannot sustain any more cycling, so they just buckle. We call it buckling. So they just deform out of plane, and by doing that, they cause concrete crushing, as you can see here. So we were just removing the sensors because the wall was completely damaged, and we didn't want to damage the extensive sensors. So we just stopped the test, we removed everything, and then we continued up to 4% drift ratio, that is roughly 4 inches displacement at top. And gonna pause it here just a moment. Okay, here I want to show you that a big hole opened into the wall. I actually put my hands in. I mean, it's not really safe to do. Yeah, please go ahead.
So the load is actually oscillating between positive and negative?
Exactly. So,
1 point.
so this is the displacement that produces at the end is like a load. So we apply a displacement at the top, which causes a load response into the wall. And this is cycling between positive and negative. So it's like we are pushing and pulling the wall.
Constant force? Like in a, I mean, that's what the building would experience?
That is called simulated earthquake loading, because during an earthquake, you know the displacement is at the bottom, right? So everything shakes from the ground. In our experiment, the bottom was fixed, completely fixed. Here, there was a footing that was fixed. What we were moving was the top to simulate the effect of an earthquake. Yeah. So the result in terms of damage and the load displacement curve is what you can expect during an earthquake. Sure.
Would the loading be in a different direction if the wave of the earthquake was traveling in a different direction relative to the wall? But, you know, I would imagine walls flapping back and forth out of plane.
Depending on the earthquake, the direction of the wave may hit the building. So the wall is just a component of a building. So it may hit the whole building at an angle, and this can create 2 waves, basically, maybe one longitudinal, one orthogonal, right? You can kind of decompose it. So the one that would be in plane would be like this one. And then there may be other effects. Yeah. Thank you. You had a question?
Yeah.
Yeah.
Gloria, yeah. The percent of drift basically is the drift of the actuator, right?
Is the drift of the wall. So
of the wall, and what is constant in the actuator is the displacement.
It was the rate of displacement. It wasn't actually constant because it was lower at the very first amplitude. It was really slow, okay, because we didn't know what to expect. So in this type of testing, you go really slow at the beginning because you may get a global failure right away. So we need to be cautious to go really slow. And then once we get the desired response, once you start seeing cracks that go the way you desire, then it's like reassuring. You say, okay, the wall is gonna hold. And you increase the amplitude of the drift, and you increase also the rate of the application of the displacement. Yeah. Any other questions? Okay.
and no axial force.
This wall was tested without axial force. So squat walls that are these low aspect ratio walls usually don't carry heavy load because you may find them in lower buildings, so there's not much on top of it, so the axial load is kind of limited. But we tested another one with 10% axial load to simulate the effect of what you have above a wall, basically. Yeah. Yes, this work was performed at UCSD in collaboration with Hilti, and I'm really thankful to all the lab staff at UCSD. Okay, great. So exciting test and exciting result. These are the pictures of the final damage of each of the tested walls at the end of the test. So you can see a lot of concrete crushing, a lot of diagonal cracking in this type of walls. These walls need to be also restrained. You see these chains because it was completely unstable, so we had to restrain it at the end of the test. And this is the slender wall. So despite the difference in geometry, we were able to identify the most damaged regions that are kind of common for all walls. And specifically, these are this fold region here that we call it plastic hinge length. It goes from the base of the wall up to about half of the wall length. So if you take this dimension here, this is the wall length, you take half of it and you measure it from the base of the wall, you get around here. And this is the region where the majority of the damage will occur. And this is regardless of the type of wall that you consider. Instead, specifically of the type of wall, we can get different damage zones. Like these low aspect ratio walls, the diagonals are really critical. In the slender walls, the columns are more critical. So you see a lot of damage, and may be also difficult to quantify in conventional ways. So we'll see applications later on how to best quantify it. So what can we do now? We wanted to work toward the seismic resistant structures and systems. So we want to assess the seismic hazard of our buildings and build a better resistant seismic structures. So we can start from a large-scale structural testing the one that we saw just now, and we can use the data that we collected here to improve our numerical modeling tools. So we can, after good predictions are reached here, we can work toward improving design code, and everything will help us to build seismic resistant, reduced damage structures and systems. So really nice. You may ask me now, what should we do? So
well, I was going to ask you something else. I mean, I see it different. I see that you actually, from data collected over time for earthquakes, you can actually develop a computational model that will actually improve your testing.
Yes, so this is a bi-directional way. So indeed, the story went the other way. As you said, I used first numerical modeling to predict the results of my testing. And then I also used the numerical modeling after a test to validate the result. So of course, this is a relationship that goes in both ways, of course. Thank you so much for the clarification. And this is where I think your expertise, your computational skills would really help earthquake engineering, because these modelings are not super simple. They involve nonlinear behavior of the structures, so it's not. There's still a lot of improvement needed in this sector. So let's take a look at this. So the software I use is OpenSys. Do you know OpenSys? No, no. Okay. So it stands for Open System for Earthquake Engineering Simulation. It's an open source software, so everyone can use it, it's free, and everyone can contribute to the software. So if you don't like a material model, for example, you can build your own, you upload it, and all the research community will be able to use it. So it's a really nice tool. And it's a finite element model for advanced simulation of nonlinear behavior of structural systems. So it allows us to predict the behavior of nonlinear structures during earthquake motion, for example. It is maybe written in C++, and it doesn't really have graphical interface. It has like a code-based interface, but it's really simple. It's okay. It's good. It's nice. This is the framework that the main framework of OpenSys. So we have a model builder module here. This is where you put all the information regarding the building, the materials, the geometry, the loading conditions, and so on. And this is communicated with the domain, which is where the state of the model at time t and at t plus delta t is saved. Then we have the analysis module. Here we have all the solution algorithms. We have information regarding the equations that we need to solve, how are they organized, and so on. And this is the module that allows us to move the model from the state at time t to the state at the time t plus delta t. And then the last module here is the recorder. Here we describe all the parameters that we want to save. So for example, if you think of my walls before, we were seeing the load versus displacement curve. So in this case, we will need to save the load and the displacement of the node of the wall. And this is connected to the domain, so that we can save and look at the data once the analysis is done. And so there are many models within OpenSys you can use. You can select your own model. You can also build your own model. I used a model, a 2D fiber-based model that was developed by Professor Colloquium. It's called multiple vertical element line model, and it's able to capture also this shear flexure interaction behavior of the walls. So remember at the beginning I showed you that there are two main types of response of the wall. One is more flexural and one is more shear related. But usually in walls we have both of them. So a model that is able to capture this interaction is really helpful because it will get better prediction. So you see here a wall. This is a wall model. So the wall is discretized in a series of elements. We have you can decide how many elements to choose along the height of the wall. So these are the elements 1, 2, and so on. And along the length of the wall, so on the x-axis here, you can select how many panels to use. So the panels are these rectangles here. And these are called the reinforced concrete panel because they model the behavior of the concrete and of the reinforcement. So the material models are incorporated within this panel here. So you see reinforced concrete is made of concrete and reinforcement. So we will have two material models. This is the material model for the concrete. It's kind of complicated. It's highly nonlinear. So a change in the x direction doesn't really relate to a change in the y direction. So it is called a nonlinear. Here we see stress versus strain. I don't know if you're familiar with the stresses and strains. Are you? Okay, great. Thank you. That helps a lot. So we can also see that the concrete has a non-symmetric behavior. So when we compress the concrete, imagine you have a concrete cylinder and you push it this way, the concrete is really strong. On the other side, when we pull the concrete in the other direction, we don't get as much strength as in compression, and we will start seeing a cracking. So the concrete in tension will crack, and with time it will degrade and deteriorate, and the capacity of the global structure will be reduced. Thankfully, the modeling for the steel is simpler. This is the reinforcement steel. It's symmetric in tension and compression, so that helps a lot. And it's usually modeled with a bilinear model. Yeah, so simplified as a bilinear curve. So one slope here and the other slope here. So these are included at the panel level, then the response is computed at the element level, and then combined to give us the response of the wall. Yes?
Can you give us an idea of what magnitude of the stresses are in that top, sorry, the strains are in that top graph?
For the concrete?
Yeah. You know, 2% or?
Yeah, about that, 2–3%, yeah.
And is that steepest curve on the compression side, is that the initial? Does this show
Yes.
like processes of breakdown or plastic deformation or something?
Yeah, this is the initial stiffness. Yeah, the slope of this curve is the initial stiffness of the concrete. And this is kind of inverted. Here we have compression on top and tension at the bottom.
So,
Yeah.
question. So the steel here doesn't have any buckling, right?
No,
Oh, that's
that's a big thank you so much. This anticipates one of one of the main questions. Yeah, that's a very good observation. And I will show you in a bit. So, as we said before, having experimental data will help us improving numerical models and vice versa. This is an example of the mesh that I used for my low aspect ratio wall. I considered 8 elements along the height and 8 elements along the length. So these elements were 12 inches by 12 inches. You can select the dimensions and based on what results you want to get. And the geometry is really simply defined by this coordinate of the central node. So the geometry of this wall is literally the coordinate of this node here. And we define a fixed node at the base that is simulates the foundation that doesn't move, and a control node at the top. This is where we apply the displacement history. And these are the results that we obtained in terms of global response of the wall. So the curve that you saw before, lateral load versus drift. In black, you see the numerical prediction, and in gray, you see the experimental result. So what can you tell me? Do you like this model? It's good, right? But it's quite good, especially up to peak strength. That is the maximum value of load that we measured during the test. After that, we see that the black curve still goes on, and the gray curve is not, because the wall is failing. And specifically, what we observed that these values of displacement were a lot of concrete crushing, big concrete cracks, and as Ignacio pointed out, buckling and reinforcement rupture. And since this is a 2D model, so it's just in plane, these behaviors are not included. So this is a limitation of the model that I used, because as engineers, we want to know the maximum load that the wall can withstand. But if I just look at the black curve without knowing anything about the real behavior, I wouldn't be able to know which is the maximum load. Is it this one? Is it this one? We don't know. So a good numerical tool should tell us, as engineers, should tell us what is the maximum load that we can expect. Because with that, we will be able to design all the rest of the structure and all the rest of the element of the building.
Stochastic model of the spacing.
But even in this case, why not 3D? I mean, you're not gonna capture.
You can use it. So one of the main reasons why I choose this model is because it's really simple. As I said, the geometry is just.
No, I understand, but could be it's 2D.
This is 2D. Yeah, you can go and try to use.
No, I know I could, but why you didn't use a 3D instead of a 2D?
Because for the simplicity and the really time was really fast to use this model. It was really simple. It was right available. So it had a lot of good. I think, yeah, for us it was the best model to use at the time. It was really fast. It gave me quite good predictions. If you look at the load capacity, is quite good. You only don't know the maximum load, but the accuracy is really good. So I didn't go into a 3D model because first of all, for timing was the main reason. Yeah. Other questions? Okay. So work in progress, I would like to improve my numerical modeling. So we could include a still model, for example, that captures degradation. So this is the still model that I used so far. And you see the slope of this line is not decreasing. So it's not really capturing fatigue and degradation. But luckily, OpenSeas has a lot of material models. There are a lot of researchers that contribute every day to advancing this software. And there is this still model that instead, as you can see, is reducing the slope. So this model here, once you set certain parameters, will be able to capture still degradation. So these may improve our numerical predictions. Okay.
So is that plastic deformation that you see on those long horizontal lines? Is that what
Here.
Yeah, the relatively flat parts of this curve.
Yes, it may be. Yeah, it may be classified as plastic deformation. The reinforcement after a while doesn't return to the same original status. So, yeah. Okay, so ready to move to the other part. So this was just an application. The second application I'm going to show you is the laser scanning techniques. What is laser scanner? So laser scanner is like this scanner here. It captures digital information of an object by scanning by using a non-destructive laser light. So it scans whatever it has in front of it, and not only in front of it because you can rotate. And it captures millions of points to characterize an object. So it gives us a 3D coordinate of the point and also photographic information regarding the color, so the RGB color of the object. All these, you can produce many scans, and all these scans are then stitched together to create point cloud data, which can be used for various engineering applications. And three main things: laser scanner techniques are very accurate. We can reach resolutions of the order of millimeters. They can capture millions of data points per second, so they're kind of fast. And they're cost-effective, efficient, and they provide a lot of mobility. So we thought, why don't we test it with our walls? And this is what we did. So this work was performed in collaboration with Dr. Wang during his postdoc. Here you see a reproduction of the scene of my test at the end of the wall shaking. And this is the exact laboratory, how it looked like at the end of the test. So we collected about 16 scans of the walls and of the surroundings of the walls. And then we aligned all them together with respect to this common reference system, X, Y, and Z. And we were able to reproduce this 3D picture, 3D state of the walls. And so this data needs, so we have all these, imagine these are all coordinates, 3D coordinates of points, and we can play with this point. We can refine the registration, for example. So you see here on the left, this is me actually taking pictures while the laser scanner was scanning the walls. I was going around the wall and taking pictures, and it's not really, it wasn't important for me to be there, right? So I I was removed. These are not points that we're interested in, so we can just remove this point and get a cleaner definition of what we're interested in, which is the wall. So this wall has about 15 million points. It's defined by about 15 million points. And then we can also look at the parts of the wall that we are interested in. So in this case, the face of the wall where we had the majority of the damage. So this may look like a 2D picture, but it is indeed a 3D scan. If you rotate it around, you see also the depth of the surface of rupture. So that's an interesting information that is difficult to get with the conventional sensor and instrumentation. So this is a really cool application. And then we can focus on the regions that we're interested in. For example, if you look at this yellow rectangle, this is this cone of rupture here. We can identify the boundaries and applying some algorithms to clean the boundaries, like in this case, and at the end get an estimation of the area and of the volume. So this is really interesting because I challenge you to get the area of this region. It's not a regular shape. It's really difficult to get the area and the volume of how much concrete was removed from this region here during the test. With the LiDAR scanner, with the laser-based techniques, it is relatively simple. And another interesting application is the detection, well, the estimation of the relative displacement. So with all these data points that we collected, we were able to estimate how much the residual displacement was. So here we see the top beam of the wall, so this part here, which is not straight anymore. At the end of the test, it is not straight. You see, it has like a tilt angle. And this is the residual deformation after the earthquake event, if you want to put it this way. And with the LiDAR scanner, we can estimate the tilt angle and the differential displacement. To conclude, another really cool project that I think you may be interested in is the use of drones to estimate the displacement after events or also during earthquake events. So we can fly these drones also in regions where we cannot really, we don't have access. So imagine, for example, post-earthquake reconnaissance. There may be buildings that are not accessible because they're classified as dangerous. They may collapse sooner or later. So engineers cannot enter, but drones can fly over it. So we can collect data and information using drones. This is a work that was performed by Dr. Wang a couple of years ago and showed us really promising results. So in conclusion, I would say let's have fun. If you're interested in collaborating with me, you can send me an email here. These are pictures of me in the lab. It was really fun. So I just wanted to share with you. Thank you so much for your attention today.
So we have some minutes for questions, 10 minutes. So any questions? Yeah.
OpenSeas, what operating systems is it compatible with?
Both Mac and Windows. You can use it. I think.
And by implication, Linux. Because if it's applicable to Mac, because that Mac is a Unix system.
I'm sorry.
So,
Mac is a Unix OS. So I'm assuming it's if it's compatible with a Mac, then it's compatible with any Linux.
Honestly, I'm not really. I only have Windows, so I never used it in a Mac. But I think it may work. I'm not really sure. We will need to check. But I think it may be compatible. Yeah. I don't recall now, but we can look at
It
it.
would be surprising if it wasn't. I mean, if it works on a Macintosh, it's generally Linux, because anything on Linux will work on a Macintosh.
Mm-hmm. Yeah.
How many drones does it take to do 3D reconstruction?
Well, the drone has a camera that already gives you, 2D. It can also be one, depending on how many times you fly it around and which flight path you decide. But
Okay, but it has to have a certain number of trajectories.
yes, you need to select the trajectory, and you need to be careful that you have enough data that kind of overlap. So don't leave any kind of blank spaces in between, so you can really reconstruct the full picture. Like with the laser scanner, we did probably 16 scans because we didn't want to leave some like kind of blank spaces in between. We need multiple overlapping regions. We need redundancy to get the best results, basically.
What does cost effective mean on a laser scan?
Because well, recently
It used to be expensive, that's all.
yes. However, this is probably more related to construction sites. So recent applications of laser scanner. Now, recently, laser scanner is used a lot in construction sites. So they can monitor all the progression of the site with the laser, and they can reduce the cost that probably would cover an employee or a worker that was taking note of all the progression, was analyzing everything. With the laser scanner, it's kind of optimized, and you can reduce the costing this way.
Yeah, what software stitches it together?
You can do it in MATLAB. There are already built-in algorithms in MATLAB. Yeah.
So they have a toolbox for this.
Exactly. Yeah. Yeah. It's called the point cloud data analysis, something like that. Yeah. Great.
If you check it, then anybody has a question, you need to stop sharing.
So good.
Any question up there? Let's do this.
I think they're fine.
So in the meantime, I have a question.
Yeah.
So it's just curious. When you were showing your first slide, your second slide, you were showing examples of Northridge, Mexico, like 85, and Kobe 95. I remember when I did my undergrad and I learned about structural analysis, always were exactly the same example. Kobe, Mexico, and Norwich. Why? We have the Japan 2011, we have Sumatra 2004, we have Chile.
Those are like the key historic earthquakes. Well, Northridge was really important, especially here, I would say, in terms of standard.
Yeah.
It really woke up the community. Really, it was literally like an eye-opening because many things that were thought as working didn't work. So
especially Mexico in the 85 also, everything just.
And that's a big change. A lot of construction codes and all kind of stuff. And they also started retrofitting. bridges and all kind of things.
And also
Or changing
looking,
the eigenvalues.
Basically.
and also looking at things that they didn't look before, like anchors, for example, the connections that I put in my wall, they had a really significant advancement after Northridge.
Especially with that collapse that they had.
So you have a question over there.
No, that's me.
Oh, that's you.
I asked questions, but they didn't reply.
Yeah, and not only the greatest one, but for example, Haiti in 2010 also, it was a magnitude 7.8. I think that the damage was like catastrophic.
Yeah, there is still a lot that we need to learn for sure.
I always was complaining with my professor at that time because I'm from Valdivia, next to the 1960, which is the greatest. And in the university, nobody was talking about that area. I was saying, come on, that is the greatest. But yes, I was even pay attention to those things.
Yeah.
So does this mostly have to do with analysis of existing buildings, or is this? It seems to me like if people are going to build a brand new building, they would make sure the probability of failure would be very low. Right? So So is this mainly about like looking at old structures that are still, that like, and trying to assess the probability of failure of those? Or is this also like inform new buildings as well?
Well, this is a numerical tool that can be used for both. Can be used both for, well, to be honest, if you go into an industry firm that designs new buildings, they won't use probably OpenSeas. They have different softwares. OpenSeas is more for researchers, and we may probably look more at existing structures. Yeah. But once you have a good tool that is free and works really well, why not using it also in industry, for example? Let's bring OpenSeas to the industry.
More questions?
With my tankers.
Okay, so thank you very much.